In this video, we're going to learn about Le Chatelier's principle. So Le Chatelier's principle states that when a system that already is at equilibrium is disturbed, the system will shift its equilibrium position in order to oppose the change that was made. Now, this doesn't change what K is necessarily. However, either more products or more reactants will be produced as a result of some disturbance to the system. So let's consider concentration change effects and how that plays out with Le Chatelier's principle. So if the concentration of reactants increase, then the system will shift rightward to produce more product. So consider this equilibrium where we've got H2 and I2 at equilibrium with HI. Let's say that there's some H2 and some I2 and some HI, and they've reached equilibrium, and now the concentrations should be constant. And let's say that we add a little bit of extra H2. We inject that in from some external source. So our concentration graph would look like this. Over time, you can see at time equals 0, we're at equilibrium. The concentrations are not changing. But then after 10 minutes, say, we inject the system with a little bit of extra hydrogen gas. So the hydrogen gas concentration obviously spikes as we've just put that in. And then what happens is the system shifts to oppose that change. What happens is that the concentration of H2 will decrease to an extent. It won't necessarily go all the way back to where it was, but it will decrease. And the concentration of HI will increase, HI being the product. So note that if we've added some H2, that will start getting consumed more. It will also consume some I2, which is another reactant, and that's why that reactant, both reactants really, will decrease their concentrations, and then the HI will increase in concentration. And then at some point, they reestablish equilibrium, but note that the exact concentrations are going to be somewhat different than they were initially. Note that Q is back to being equal to Kc. That's because we're back to equilibrium. But the concentrations, I should say, at equilibrium are somewhat different now that the equilibrium that previously existed has been disturbed. So a good way of just sketching this out. Look, we have an increase in the H2. This will result in an increase in the I2, the HI that's produced. The system will shift rightward. We get an increase in HI produced in order to reestablish equilibrium. And it's also worth noting that in addition to increasing the concentration of a reactant, you could also shift a reaction forward, rightward, by decreasing the concentration of a product. And actually, a good example of this is if you've got some hot coffee, just blowing on it. Coffee, of course, there's water in the liquid state and water in the gaseous state. There's some equilibrium there. It's known as vapor pressure. And if you blow on it, you're blowing away the gaseous water, which actually is reducing the amount of product. If we have this equilibrium of H2O in the liquid phase at equilibrium with H2O in the gaseous phase, if we're decreasing the concentration of H2O gas as we blow it away, the reaction shifts to produce more and more of this. As this gets removed, more and more of it's produced. And actually, theoretically, you can really start noticing a decrease in the volume of your coffee if it stays hot and you keep blowing on it. On the other hand, if you decrease the concentration of a reactant or increase the concentration of a product, that will have the effect of shifting an equilibrium leftward. So temperature also is something that can change. And of course, temperature is something that affects the equilibrium constant anyway. But you can make predictions as to how equilibrium, not only how the constant will change, but also the direction that equilibrium will move towards based on whether a reaction is endothermic or exothermic. Let's take a look at an example. If we treat reaction enthalpy as either a reactant or product, then we can get a little bit more of an insight looking through the lens of reactants from products as we did in the previous example. So let's say that we've got water at equilibrium with steam. We know that water, when it boils, that is an endothermic process because bonds are being broken. So what we can say is that this 40 kilojoules per mole that are required to make water vaporize, that's also known as the heat of vaporization, um, that energy can be treated as a reactant because it's put into the water. So we can kind of look at it like water in the liquid state plus 40.67 kilojoules per mole gives us water in the gaseous phase. And with that in mind, if we were to increase the temperature, it's kind of like increasing this input of energy at the beginning. And so if we raise the temperature, that will shift the reaction, that will drive the reaction forward. Um, and this is actually why vapor pressure will increase as you raise the temperature. Vapor pressure at, say, 5 degrees Celsius is pretty low, but as soon as you get up, 70, 80, 90 degrees, we're approaching atmospheric pressure being equal to vapor pressure. And that's all because you're raising the temperature, you're making the equilibrium move more towards the product side, the gaseous side. Um, but on the other side of it, if you lower the temperature, then the equilibrium will shift leftward. Surprise, surprise. If I have boiling hot water at about 100 degrees Celsius, if you cool it off, well, then you're going to see a lot less steam over it. You'll see a whole lot more liquid water. On the other side of things, for an exothermic process, we have H2 and N2 forming NH3. This is an exothermic process, and so we would treat the heat as a product. So we could draw it out kind of like this here, where the 92.32 kilojoules per mole, that is the enthalpy of reaction that's shown as a product. So if we raise the temperature for this reaction happening, it will actually shift the reaction equilibrium leftward. But if you do it at a lower temperature, then the equilibrium will shift towards the right. Next, we have pressure. And pressure is complicated because, well, okay, if we change the system's volume, then that's not, I mean, it's changing the pressure, right? If we have a bunch of gases and the volume in which they are contained is changed, then the concentration of gases will change. So, for example, if I've got a box and there are some particles in it, and then I squeeze the same number of particles into a smaller box, then the pressure is in this small box is going to be higher than the pressure in this box. Also, the not just the pressure, but the concentration will be higher in this box than in this box. And this actually, you can look through this lens to make predictions based on concentration. But in general, what we can say is that if the volume of a system is changed, then the concentration of gases will either increase or decrease proportionally. Concentrations will increase if the volume is smaller, they'll decrease if the volume is raised. And if the pressure increases, then the equilibrium will shift towards the side with fewer molecules of gas. That just happens to be the way it works out. But again, you could look at this through the lens of just your changing Q. If the pressure decreases as a result of volume increasing, then the equilibrium will shift towards the side with more molecules of gas. And so a good example that we can look at is a can of soda. The solubility of carbon dioxide gas, I mean carbon dioxide, which could be a gas, it also could be dissolved. The solubility depends on pressure, and we know this because there's a whole lot of gas, a lot of carbon dioxide gas that can bubble out of soda, a can of soda, once you've opened the tab. Until that point, though, the the soda is at a high pressure, and the carbon dioxide is held under high pressure, and the carbon dioxide is very soluble. So what we find is that under high pressure, the equilibrium really tends more towards the left side. But once you lower the pressure, then it's going to shift massively to the right, which is why we get bubbling of carbon dioxide gas out of a can of soda once you've released the pressure. And that has to do with the fact that once you release the pressure, um, the equilibrium will be favoring the side with more molecules of gas, or at least it'll push more in that direction. And so finally, another detail that's really important, people often mistake this. So if you were to push an inert gas into a system that's at equilibrium, this of course is going to increase the total pressure. Say you've got 5 moles of gases that are involved in the reaction in a certain volume, and then if you add another 5 moles of some inert gas that isn't involved in the reaction, obviously the pressure is going to raise. You have 10 moles of gas now. However, the partial pressures of all reactants and products are going to remain constant. You have an added reactant or product, so the partial pressures will remain the same. And as a result, the equilibrium will actually not shift. So, bottom line is the addition of an inert gas has absolutely no effect on pressure, but injecting a reactant or product will, and also changing the concentration of a reactant or product by changing the volume in which they're held, that will also affect equilibrium position. So that is all for Le Chatelier's principle. I hope this video has been helpful. Let me know if you have any further questions or comments in the comment section below. Thanks for watching.